Okay, folks, this video is from section 4.4 called Indeterminate Forms and L'Hopital's Rule. Okay, so an indeterminate form is a particular form or expression that we get upon taking a limit of a ratio. And then if we get an indeterminate form, then this rule, L'Hopital's rule, is a method to sort of simplify or change the expression and then try the limit again. Okay, so an example could be something like this. The limit as x approaches 1 of natural log of x over x minus 1. All right. So, as always, when we're faced with a limit, first thing to try is direct substitution, right? Try plugging it in. Maybe you'll just get a value and it'll be done. So let's try plugging x in as 1. So let's say ds to indicate that. And so I'm going to get natural log of 1 divided by 1 minus 1. All right. Well, 1 minus 1 is going to give us a 0 in the bottom. And the natural log of 1 is also 0. All right. So we ended up with this limit that looks like, upon direct substitution, we're getting this form 0 over 0. 0 over 0 is one example of what we call an indeterminate form. It's sort of indeterminate. It's not determined. We don't know if this limit exists. We don't know that it does not exist. We don't know that it does exist. We really don't know anything at this point. We've got this indeterminate form. Let me just mention though, first of all, 0 over 0 is not equal to 0. So this definitely does not say that the limit equals 0. Definitely does not say that. It also does not say that the limit doesn't exist. And again, I said that a second ago, but sometimes students struggle with that because if you try to calculate that as a number, 0 over 0 as a number does not exist. However, the limit might still exist. We might have something else to do. We've seen examples like that. So if I said the limit as x approaches 3 of x squared minus 9 over x minus 3, right? We've looked at examples like this where I try direct substitution, I get 0 over 0, indeterminate form. But I can factor the top, right? We have other methods. I can factor that top as x plus 3, x minus 3 over x minus 3. Try that limit, right? We can cross off the common term, which is using our replacement theorem. Now we can do direct substitution. 3 plus 3 equals 6 upon direct substitution. So we had 0 over 0 originally as an attempt trying to do direct substitution. But we found that the limit actually does exist, and it's just some number 6, right? There's no way of telling the number 6 from this expression. So that's what it means in indeterminate form. In this case, when we ran into that form, we didn't have L'Hopital's rule yet. We didn't know what that was. But we had a technique, in this case, factoring and using our replacement theorem, that we were still able to evaluate this limit, okay? So that just goes to show that 0 over 0 doesn't mean the limit doesn't exist. It might still not exist, but we have to look further. We have to use other techniques. So replacement theorem was one technique. On paper homework number 1, you looked at this limit as x approaches 0 of sine of x over x. Same idea. You try direct substitution here, you get 0 over 0. Right? So it's always worth a shot. However, when we looked at homework 1, we found, paper homework 1, you looked at various ways of looking at this. We graphed it on Desmos and used the graph to see, it's undefined when x is 0, so there was a hole, but we could trace where the graph was heading towards as x approached 0, and we saw that the limit was equal to 1. All right, and then we did this also looking at a table, right? As x is approaching 0, and maybe it's 0.1 and 0.01, 0.001, right? We plugged in smaller and smaller values into a table, and noticed that the function values were approaching 1. Okay, so the fact that we get an indeterminate form, in the previous case it equaled to 6, the actual limit here it equals to 1. So what are some other techniques now that we can use though? Because here I don't see there's nothing I can factor up top, right? So how am I going to get this to work? So the way L'Hopital's rule works, it says it says a big mess about if these functions exist. First of all, what you need is a ratio here. Right, so I'm thinking I've got this top function I'm thinking of as sort of like f, and I'm thinking of g. As long as both of those functions are differentiable, what we're claiming is that the limit as x approaches some value, in the book they call it a, of some function f of x over g of x, right? And I guess you can apply L'Hopital's rule other times, but you really only need it if you get the indeterminate form. If I'm trying to take this limit and I end up with an indeterminate form, then what I can do is consider the ratio of the derivatives of these functions. So instead of looking at the original function f, I can look at its derivative over the derivative of g. and try that limit. Okay? And what L'Hopital, so this is L'Hopital's rule. This is sort of the conclusion that says that the limit as x approaches a of this ratio will be the same as the limit of the ratio of the derivatives if this limit exists. This limit exists, all right? So you get something in determinate form, sort of inconclusive. What do? Let's try differentiating the top, then differentiating the bottom, then look at that ratio, try the limit again, see what happens. Sometimes you might want to apply or might need to apply L'Hopital's rule again. Other times the answer is going to fall out right then and there. Alrighty. Before we go on to this first example, let me just mention, in class I talked about this a little bit. I mentioned, talked about the quotient rule. Someone emailed me right after class asking, is this related to the quotient rule? And it is not. This is not related to the quotient rule. It seems that way, maybe, because I have a quotient, right? I have a ratio here, and then I've got a ratio. But remember, the derivative of a ratio is not this. It's not just the derivative of the top over the derivative of the bottom. So what we're doing here is we're using these individual derivatives. Essentially, a derivative tells us the rate at which the original function changes. So here we want to know, in this case, natural log of 1 is approaching 0. This x minus 1 is approaching 0 as x gets close to 1. What we're going to do when we take the derivatives is see, yeah, we know they're going to 0, but we want to sort of see how fast they're getting there, right? At what rate are they approaching 0? And the derivative tells us the rate of change. So that's the idea right there. So it's not the quotient rule. It's unrelated to the quotient rule. The quotient rule is when we've got a function, let me call it q of x, that is a derivative. Got a function that is a quotient. And we do use the f and g right there. But in that case, we're trying to find q prime of x, right? We're trying to find the derivative of this thing. That's not what we're doing here. Here we're just trying to find the limit. Just trying to see where the function is going to as x gets close to a particular value. So unrelated, it utilizes derivatives, but really we're just looking at limits here, which we did early in the semester. Okay, so again, there's some write-up in the book, so maybe read through it. I won't write all. I'll write down the other indeterminate forms. But basically, if you try a limit and get an indeterminate form, then as long as both of these derivatives exist, and there's some caveat that this derivative shouldn't be 0, right? We don't want to divide by 0. But as long as everything's working nice, then this limit will be the same as this limit. So let's look at it for this example. What this says now is that the limit as x approaches 1 of natural log of x over x minus 1, so I'm kind of recopying the original limit that we're looking for, is equal to, through an application of L'Hopital's rule. So let me just indicate that that's what I'm doing here. I'm saying this limit is the same as this limit because of what L'Hopital's rule tells us. And so the derivative of natural log of x is going to give me a 1 over x. All right, and then the derivative of this is just a line with slope of 1. So the derivative of the x is going to give me a 1. The derivative of the constant is 0. So I have 1 over x over 1. All right. Is that looking correct? Sure. And now what can we do? Can we take the limit now? Can we evaluate it? So again, as always, try direct substitution. Earlier, we were getting 0 over 0. We had that indeterminate form. Now what's happening when we do direct substitution? Well, now as I let x go to 1, this reciprocal of 1 over 1 is going to become a 1. My denominator there is a 1. And so the answer is 1. All right. So kind of interesting. Again, there's no way to glean that from this. This thing just tells us that we have to try another technique. And the technique we want to try is L'Hopital's rule. And then lo and behold, the limit does exist, and now it equals 1. Okay. For all of these things, it might be nice to graph, we call it q of x, but graph on Desmos natural log of x over x minus 1 and verify visually that the limit is 1. Okay, you'll see a hole because, again, q of 1 here, if I'm calling it q, doesn't exist because we still can't divide by 0 for the actual function value. But the limit, as x gets close to 1, the function should be nearing the height of 1. So you can, if you're thinking, does this technique really work, check it out and look and see for yourself. Alrighty. There we go. Let's do another few examples. So some other examples from the book look like this. X squared minus x over x squared minus 1. All right. And do we want the limit as x approaches 1? Okay. We're told to do the limit as x approaches 1 here. Let's see what we can do. So if I just plug one in, direct substitution, worth a shot. I always do this as my first shot. I'm going to get 1 squared is 1 minus 1, and down here I'm going to get 1 squared minus 1. Going to get 0 over 0. Alrighty. Is there anything I can do factor-wise? So let's say the limit as x approaches 1 of x squared minus x over x squared minus 1 equals, let's try like a replacement theorem, something that we might have tried. So before we apply L'Hopital's, let's see if I can try this. So here I see a common x, so I can do x, and then I'm left with an x minus 1. And on the bottom here, I've got, this is a difference of perfect square, so I've got an x plus 1 and an x minus 1. All right. So in that case, I did not, I think we're going to be able to do this using the replacement theorem without L'Hopital's rule, right? Because I see that x minus 1 in the top and bottom. And if you think about it, it's that factor in the bottom that was causing the problem. Because as x went to 1, that was becoming the 0. So as we cancel those out, now this is equal to the limit as x approaches 1 of x over x plus 1. This limit is equal to this limit because of our replacement theorem. So going way back to maybe chapter 2 when we first studied that. And after we use our replacement theorem, the next thing we wanted to try again was try direct substitution. Now I can let x go to 1, and I'm going to get 1 over 1 plus 1, 1 over 2. All right. So we got the indeterminate form here. We were able to factor, so we didn't need L'Hopital's rule. However, L'Hopital's rule should still apply here because we did get the indeterminate form. Both of these functions are differentiable. So let's try L'Hopital's rule, try a second method, and see, are we going to get 1/2, right? See if it works out. So this way was using the replacement theorem. We got 1/2 as our limit. Again, I would encourage you maybe graph the entire function, graph this entire rational function on Desmos, and look at what's happening when x gets close to 1. See if you can notice a hole. You should see a hole living at that spot, right? I'm reluctant to call it a point because it's an open dot, but you should find the hole there. Okay, let's try L'Hopital's. So L'Hopital's would say that this limit is equal to the limit as x approaches 1 of the derivatives of both of these things. So I'm going to get 2x minus 1 up top, and I'm going to get 2x, just 2x in the bottom, right? Because the derivative of this x gives me the 1. The derivative of this constant is a 0. So that's what we get. And now can I try direct substitution from there? So this was an application of L'Hopital's. So just like I did with direct substitution, like I did with the replacement theorem, I like to indicate why this expression is equal to this, right? Who says those things are equal? L'Hopital says it, right? And if you're wondering, L'Hopital was a person's name, French last name. In some books, they put an S in there, like the word hospital. I think our book does that. I've seen it without the S with this little caret thing on the O, so whatever you want. But yeah, so I want to indicate that I'm using L'Hopital, so I took the derivative. Then we'll try direct substitution, and let's see what we're going to get. So now as I plug 1 in for x, the denominator is no longer 0. So that's good, regardless of what happens up top. And up top, we're going to get 2 times 1 is 2, minus 1, we get 1/2. Cool. So we got the same result. Maybe this was a little bit easier, either way, but it's nice to do things twice, 2 different ways, and get the same result. All right. Okay, so let's look at maybe 1 or 2 more examples. Keep my eye on the time of this video. So indeterminate forms are things of this nature. Get a ratio 0 over 0. Means they're both going to 0, but at what rate are they going? So if they're both shrinking, but one is shrinking at a faster rate than the other, then the limit might exist. Also, what if something's going off to an infinity, right? Over infinity. Same idea. Does that mean the overall ratio is going to infinity? Not necessarily. It could be going to 0. Could be going to a fixed non-zero number. So this is also an indeterminate form. And that could result, you could have positives or negatives here. It doesn't really matter. So if you have an infinity over an infinity, you've got indeterminate forms. Now, if you mix and match infinities with zeros in the same ratio, as far as numbers, they're not going to exist, but as far as limits, they might exist. In other words, if you have the limit of some function, let's say some ratio as x approaches some value, right? If you end up noticing that as x gets close to this value a, the top is getting close to 0, and the bottom is getting close to infinity, right? Well, what does that equal? Well, infinity is not a number, but if this is what we would get upon direct substitution, then this is sort of, we would get this 0 over infinity put it in sort of a bubble. It's not really a number, but what that tells us is the top is getting really, really small, and the bottom is getting really, really large. And both of those things have the same result. If you've got a fixed top and the bottom gets really, really large, then the result gets really small, right? You divide by larger and larger numbers, the result gets small. Simultaneously, then, if the top is also getting small, that's shrinking the result. So if the top is getting small, the bottom is getting big, the overall limit would go to 0, right? And if you had the reverse, if this thing was going to, the top was growing, so going off to infinity, if the bottom is approaching 0, now, again, both of these things have the same effect. In the denominator, getting really small, if you divide by small things, the ultimate function value is getting larger and larger, blowing up. So the function value is getting larger because the denominator is getting small. And then also, if the numerator is approaching infinity, it's getting larger for that reason, right? So this would indicate, if that was the case, then the limit would actually be infinity, okay? So, for example, let's say I had the limit as x approaches infinity of e to the x over 1 over x. All right. So I'm using this arrow because I don't want to say equals because I want to write equals number. But as x goes off to infinity, e to the x is growing off to infinity, right? So the numerator is growing, which seems like it's making the numbers larger, this ratio large. And simultaneously, as x goes to infinity, 1 over x is approaching 0. So the top is growing, which makes the ratio grow. The bottom is shrinking, which makes the ratio grow. So they're both, it's like taking vitamins and then taking steroids, right? Growing extra, limit overall would be infinity, okay? So you mix and match zeros and infinities, that means something. You get one over the other of the same type indeterminate form. So let's look at an example where we have these infinities. So let's say the limit as x approaches, we'll do infinity again, of, let's say, x squared over e to the x. Okay, so we try direct substitution as, well, let me not say that. We try reasoning it out just intuitively. You can't really do direct substitution. I can't say infinity squared, right? But as x gets larger, both of these are increasing functions. So as x gets larger, x squared gets larger, so that's going off to infinity. As x gets larger, e to the x is also growing, it's moved to the right, so that goes off to infinity. So we've got an indeterminate form. Again, that doesn't mean anything as far as the limit existing or not existing. If it does exist, it doesn't mean it's infinity. It really is just inconclusive. So since we got that, let's apply L'Hopital's. Just write L apostrophe H. And so this limit is equal to the limit as x approaches infinity of 2x, right? The derivative of x squared over e to the x. Okay. But what happens now, right? So remember, L'Hopital's rule said this limit, the limit of this ratio, is equal to the limit of the ratio of the derivatives if this limit exists, right? If this limit exists, then they're equal. But what's happening here, as x goes off to infinity, the denominator is still growing without bounds, so going to infinity. And 2 times x, as x goes off to infinity, this still going off to infinity. Okay, so we tried L'Hopital's. We had an indeterminate limit, indeterminate form. We tried L'Hopital's. We have another indeterminate form. Does that mean L'Hopital's failed? No, it just means it hasn't worked yet. Does that mean it's got to work? Maybe not, but let's try it again, right? Because we haven't, let's suppose this was the original problem. Now we have an indeterminate limit, so we're allowed to use L'Hopital's again. All right, so this is equal to, by L'Hopital's again, the limit as x approaches infinity of, now the derivative of 2 times x is just a constant 2. And e to the x lives on the bottom because it's its own derivative. And now we can let the x go off to infinity again. What's going to happen? As e goes off, again, let me use my sort of little thought bubble. Because I want to claim what this limit's going to equal something. But what's happening, as x gets really large, the bottom is getting really large. Right? So the bottom is growing, the top is 2. As x changes, as x goes off, the 2 is staying as 2. So you've got a fixed number divided by something that's growing and growing and growing. So the result is shrinking and shrinking and shrinking. And so we get 0 as our limit. All right. Just like I mentioned before, graph the original function. Graph y equals x squared over e to the x in Desmos. Trace to the right, move to the right because x is approaching infinity. So look as far as you can on the graph to the right, and you should see that the graph is approaching the x-axis, right? The function values are getting closer and closer to 0. They will never be 0 because the top and bottom are both positive numbers. So the function is always positive, always living above the axis, but it's getting closer and closer, okay? And let's think about what's going on with these. So again, L'Hopital's is saying, okay, as x grows off to infinity, the top is growing and the bottom is growing. But then when we look at the derivatives, we're saying, yeah, but how fast are they growing, right? E to the x is growing much faster than x squared. So it's getting to infinity quicker. It's getting larger quicker. So even though the top is also going to infinity, which would make the ratio large, right? If you increase the numerator of a fraction, the value gets larger. But as the numerator increases, the denominator is increasing a lot more than that. And so you got like a moderately big number divided by a really, really, really massive number, and the overall result shrinks down the function values. All right. If you took the reciprocal of this function and tried L'Hopital's, you'd have the infinity up top, because e to the x, the faster growing function, would live up top. So you might see what happens with that one. All right, let's try one more. Let's try this. The limit as x approaches infinity again of, I will do natural log of x over square root of x. Okay. So, just intuitively, natural log of x increasing as we move from left to right. Square root of x kind of looks similar, increasing as we move from left to right. So they're both increasing. So if we try direct, or again, not really direct substitution, but try thinking about the end behavior of these graphs, we're going to get infinity over infinity, indeterminate. So that means let's try to use L'Hopital's. So L'Hopital's says let's take the derivative of the top. Derivative of natural log of x is 1 over x. The derivative of the bottom is 1 over 2 root x. All right, and so we want the limit as x approaches infinity of that. Okay. So remember, the original indeterminate form we just got was sort of this form, right? We got infinity over infinity, which is an indeterminate form. What happens now to this new expression as x goes to infinity? Well, as x gets larger and larger, 1 over x gets smaller and smaller, so that's going to 0. And as x gets larger and larger, again, in the denominator, then 1 divided by this large quantity is shrinking, so that's also going to 0. So now this is going to 0, that's going to 0. So we had this indeterminate form, we applied L'Hopital's rule, looked at the ratio of the derivatives, and now we got this indeterminate form. What does that mean? So now, there's a couple routes we could take. In the previous example, we said, well, let's try L'Hopital's again, right? We have a new indeterminate form, so let's just look at this limit, this indeterminate limit, and try L'Hopital's again. So you could do that. However, another thing you might say is, let me work with this. Now that I've got this expression, let me work with this. I've got a fraction divided by another fraction. I know what that means. So before trying to evaluate this limit, let me rearrange this a little bit. So this is equal to, I haven't taken the limit yet, so limit as x approaches infinity of, I've got 1 over x, divided by a fraction means multiplied by the reciprocal, so times 2 root x over 1, right? That's what I'm looking at now. And what's going on with that? Let me simplify this. So these 1's up top, let me just attach these. I'll multiply top by top, bottom by bottom. So I've got 1 times 2 root x is just 2 root x. And I've got just this x times 1, or just x on the bottom, okay? So rearrange it, flip and multiply, simplify. Now, if we let x go to infinity, then I'm going to get infinity over infinity. So that doesn't seem helpful yet. However, can I do any kind of cancellation? So yeah, I can. And you could do this a few different ways. You can convert the radical to a 1/2 power and think of what this is. However, I've got an x down here, right? I claim x is square root of x times square root of x, right? That's how square roots work. Square root times itself gives you x. So x is that, and now I can go ahead and cancel. So when I cancel, I'm really invoking a replacement theorem here. So limit as x approaches 0, limit as x approaches infinity of this ratio is equal to the limit as x approaches infinity of the cancellation, which is 2 over root x. Indicate replacement theorem just for good measure. And what's happening now? Now I've got a constant up top. As x goes to infinity, square root of x is also going to infinity. So a fixed number over something that's getting larger and larger and larger means the overall ratio is positive but getting smaller and smaller. And so we get that limit of 0 again. Okay, so we only did one application of L'Hopital's, and then we just did some simplification. So that route might work. What would happen if you kept going with these things and tried L'Hopital's again? I think you're going to dig yourself into a deeper and deeper hole. Because what would you get if I tried to do it again? The derivative of 1 over x is going to give me negative 1 over x squared, right? This thing is, I've got a 1/2 times x to the negative 1/2, right? That's what this is. So if I take the derivative of that, negative 1/2 times this 1/2 is going to give me negative 1/4 times x to the negative 3/2, which I can put back down there in the bottom like that. So if we take the derivative of the top, derivative of the bottom, try to apply L'Hopital's again, things are actually kind of staying bad and getting uglier for us. The fact that I have x in the denominator means 1 over x. As x goes to infinity, this guy's going to 0. X in the denominator, this is going to 0. Right? Same story we had with this expression. So could I now flip and multiply and try to combine it to what I did with that stuff? Probably. But anyway, so that shows when you can, you kind of want to have like your algebra brain ticking, or your old style thoughts of how to simplify expressions can come up. But L'Hopital's rule is pretty powerful. All right, folks.